Are we ready to go? Okay. So quick convergence. Like I know all you guys are excited about t-SNE now. You will probably put it to use to all your data sets. So what do you do to make it work? So this is somewhat going outside the paper, taking kind of everything which from different papers and putting them together. Some of it works out of the box. So if you use scikit-learn, basically the default values are this. But if you want to play around, you should know what is your parameter space you should play around. So take your data and first use PCA to have a first 50 PCA components reduction of the data. This is what the Scikit manual says, and this is what I did with the MDS data so that it looks like it looks like. So a lot of time I've seen people talk about the MDS data, they show the t-SNE, it's actually a horrible t-SNE, and they say, look, it does better than PCA. But the reason it does slightly better than t-SNE, it doesn't really visualize all the digits separately. The reason is they didn't do the PCA step. So you have to do that absolutely. And then choose two dimensions. The value sigma that I was telling you, that's in certain cases chosen to be 0.0001, so 10 over minus 4. The perplexity term has an intuition which kind of only gets clear if you read this last paper that I was looking at. It says that it's sort of related to the attraction to the nearest neighbor. So the typical range which is told is something between 2 to 50. For most typical cases I have worked on and it's used, it's set to 30. And in certain cases you might set it to 50. So ideally it's said that the t-SNE map should be robust to the perplexity chosen. What that means we will kind of talk later. So apparently Hinton has this argument that we understand that this is a we will go in that discussion, that this is a non-convex object that we are minimizing, and compared to all other low-dimensional reduction techniques which are convex like Isomap or LLE. So there is always this argument that a nice new reduction technique should be convex because it only has one solution. And Hinton argues that, well, even if you have a nice reduction technique which is convex, you end up minimizing it by approximate tools. So essentially, there is an approximation there. And the second thing he says that, what do you want? You want a great convex method which gives you bad visualization, or you want a great method which gives you great visualization? So that's an argument which we cannot beat, right? So the iterations chosen is around 1,000. Learning rate is 200. Momentum is chosen 0.5 for the first 250 iterations, and then 0.8 for the remaining. There is something called exaggeration, which is again something got developed only very late into the papers. This is only if you're very serious, this slide is useful for people. Otherwise, for most purposes, choose PCA 50 and do scikit-learn t-SNE, one step would work. So this exaggeration thing is in the very recent papers, where what they say is that they essentially exaggerate the alpha value for a certain amount of time. So the first paper said something like 3 steps: early exaggeration, then no exaggeration, then late exaggeration. And this last paper essentially says that just do early exaggeration and then stop doing it. So that's basically what I put in here. Another thing is that all these t-SNE plots, they have a seed. So the initial seed value that you have to put, I always use a seed value which is fixed, because then if you are having collaborators to talk to you, they can reproduce your result and you can see the same t-SNE plot. But in principle, remember, it's a stochastic minimization. So essentially every time you have a new map. So
Savia.
Yes.
You only have about 20 minutes left in
Okay.
total.
Okay.
So do you want to take a couple of most important discussions?
Yes, let's do that then. I will just reset it. Okay, cool. First discussion is PCA versus t-SNE. The first thing is that PCA is a linear transformation, t-SNE is a non-linear transformation. PCA preserves global order, global structure, but does not really do much for the linear structure, for the local structure. t-SNE does the reverse. We kind of went over this thing. The other thing is PCA, you can do feature engineering, but t-SNE you cannot do any feature engineering. There is no features that you can pull out. This example of Swiss roll we sort of went over. This is basically the discussion we were having, that there is, yes.
to go back to the
Yes.
so with PCA, you can use kernels to make it nonlinear, no?
Yes, there is this KPCA, kernel PCA, which you can make non-linear. Yeah.
So do you know what the difference is? Like why?
Well, the main difference is that here you have somehow a probability function which essentially maps the distances. I don't think PCA ever does that. There is a probabilistic PCA also, but then I haven't read that.
Isn't it that when you pick a kernel, you're kind of imputing that there, oh, sorry. Isn't it that when you pick a kernel, you're kind of imputing a structure onto your data? Like, you're picking a kernel that's like a Swiss roll type kernel, trying
yes.
to untangle it like that.
Yeah.
You know?
So this may or may not help. Let's say your data is elliptic in nature. In PCA, you can do.
Tell you your own point. Think about all the video.
Yeah, I was shy a little bit today. So let's say your data is elliptic. You can do a few things with PCA, including like making it diagonal, making it so that it's you can train faster, blah blah blah. You can also, if it's non-linear, you can do things like making it circular or change the shape if that helps. But it doesn't necessarily result in good visualization because that's not the purpose of it. Here you sort of kind of destroy the global structure of your data, but you make for a very good visualization.
And also I would like to add that in kernel PCA you are making an assumption of a localized linearity sort of thing, which you are not. Which you are not doing probably in t-SNE. So probably, if you look at even LLE and all, they are very refined versions of kernel PCA. That's what they say. So, what all problems we have with LLE and all kernel PCA, we would not have it with t-SNE, because that assumption itself is not there of localized linear structure.
About the assumption of local linearity, the fact that you're using Euclidean distance, doesn't that implicitly assume that at least the local space is flat?
Yes.
So I mean, it is kind of that assumption of linearity here too. Back to the geometry that we talked about a while ago.
So why it is different, I'll tell you. Because in the previous algorithms, they use the pairwise distances, as in the error was always calculated as x sub I minus x sub j minus square of that minus the L2 distance of yi minus yj, and that error used to be calculated. But here what we are doing is that we are comparing the probability associated with xij and the yij, and as he pointed out earlier in the discussion, that's where we sort of try to include the non-linearity, because we don't care about we are trying to so it's a probability of finding the point xj in the neighborhood of xi, as opposed to the straight Euclidean distance. So that's why it's non-linear approach. That's how the non-linearity is introduced. That's what he said, and that's right. That's how the non-linearity is introduced into the algorithm.
I also don't know whether this specialized PCAs, they are some specialized versions of a SVD algorithm, which is essentially a eigenvector eigenvalue decomposition, right? Whereas the way we learn t-SNE, there you don't see any diagonalization technique, right? There is a cost function minimization. It's not, but I am not aware if these kind of techniques can be mapped back to also linear algebra.
In fact, even like to add a point to his point, like when we use Euclidean distances, had we been using that, we would want, in the linear algebra, we would always want, for the diagonalization, we want it to be positive semi-definite, right? So that expectation, we don't expect that from t-SNE. So all that thing we are just taking it off.
Relaxing.
Yeah, relaxing it. So it's different. That way it's different.
Okay. Another next part one is I had promised Asan that I will have a slide on SNE versus t-SNE, but sorry for ruining all the fun because I think we have kind of covered most of this thing. So this outlier thing was an interesting discussion. SNE cost function is difficult to optimize. This is something which is essentially related to how the gradient function looks like, and the fact that in SNE there is this thing that all the far points or moderately far points, they essentially end up at the center of a map. They start to crowd a lot. This somehow, by using the t distribution, it was kind of avoided this, because it penalized somehow certain kind of distances more than the others. And
So-
right, yeah, yes.
Oh, sorry. Maybe the next slide is going to say what I was going to.
Yes, the next slide has a couple of physical intuitions. First one is that the perplexity number, for a really long time I kind of had trouble to understand what this is. Apparently this perplexity number, so what t-SNE does is it calculates attractive forces and repulsive forces between pairwise points. So let's try to get into this. This is interesting. So if you think about it, if you don't do anything special, every calculation, every of this attractive and repulsive calculation goes as order n squared, right? Because you are calculating for 2 points for all the endpoints. So now, for the attractive one, what they did was they made the algorithm faster by saying that we will not look at all the points. We will only look at a neighborhood of that black point. So that neighborhood is defined by the perplexity number, which essentially is 3. So apparently if you choose the perplexity number, 3 times the perplexity number is the number of points which you look at. And so this is again chosen, so this perplexity is related to the sigma I square by that weird like log entropic kind of function which I was having before. Second thing is, so how do you make, I'll just complete the argument. So attractive one, you can see how it got a little faster because you are not going over all the points, only 3 times perplexity points. The repulsive one essentially was made faster by this 2014 paper by saying that essentially you will use this Barnes-Hurt approximation technique, which is essentially a technique where you lose your cost function. Essentially you lose a certain amount of the cost you kind of neglect away, but that sorry, what I wanted to say was they use this the way we calculate essentially charge interactions in a map, like doing fast Fourier transform. Basically, that's the way they are essentially making that from n square to n log n by having some screening kind of a distance. So you don't calculate, you are kind of able to calculate much faster through this repulsive interaction. So maybe that was there somewhere here. Probably not. Okay, so yeah, so here you have the attractive and repulsive forces, and there are this first one which basically made the repulsive faster. Now your question.
Yeah, so this, by the way, are we still in the clarifying questions only zone? No, we're not. Okay,
No.
So, yeah, there's I think a fundamental reason
Yes.
why the T distribution works better here, possibly. And while it makes sense in the intuition that you like force stuff together with the Gaussian,
Yes.
the T distribution is what you get when you integrate your variance out of a Gaussian.
True.
So in other words, what you're saying is, I know that my like
Points are
embedded,
spread.
yeah, I know that my embedded like points should be Gaussian,
Yeah.
but I'm admitting to myself that I don't know what the variance of that Gaussian is.
Exactly.
So it's kind of like admitting your own ignorance
Yeah.
with respect to how these points should be distributed.
Yes. Okay, and this was somehow how the gradient function is a bit different in both cases. Difficult to kind of see because 0 is apparently green here and that's blue. So I think there is some difference, that there is somehow negative values here and positive values there, whereas everything was positive in that one. Okay, so what was this? Yeah, this was fine. Yes, in reduced manifold, closer points are in denser clusters and sparse clusters are less dense. So basically just because they neglect the further points. They don't map it so nicely. Scale distances, so okay, that we are kind of discussed. And size of cluster, okay. So this is, I think, most interesting, that if you have a t-SNE plot, don't try to interpret the size of a cluster, don't try to interpret the distance of one cluster from the other cluster, because they have no meaning, essentially. And this is where basically, if we ever have a talk on UMAP or diffusion map, this was kind of fixed. Weakness of t-SNE first, that it cannot be used as a general reduction technique. It is only possible to reduce in 2 to 3 dimensions. The reason is that it uses this t distribution, and the t distribution has a heavy tail. So now if you go to higher dimension, a larger part of the probability mass starts to stay under the t distribution, which essentially means that because the tails are kind of neglected in the way it's done, you are neglecting a large number of points, and essentially there is the solution to this is suggested that the local embedding efficiency is lost, so you might need to use t distributions with more than 1 degree of freedom. I haven't seen any of that being done, so that's an open kind of a problem if anybody wants to like go and pick on it. Curse of dimensionality, yeah, this is this trivial, which Vijay was saying, that as you just calculate the ratios of circle to square or circle to cube and in n dimension, and you see like more and more space is kind of the sphere essentially is in having smaller space, and it also, this is like a weird way of kind of showing that the sphere becomes a little like a clunky. Weakness of t-SNE 2 is that the local linearity assumption, that means basically that if it does not hold true, that means there is somehow intrinsically high dimensions, like I told you, images or genomics data. What do you do? What is suggested in the paper is essentially you can use autoencoders to learn through the code and then take a layer of the autoencoder and then visualize it in a t-SNE plot. This is what Karpathy did with CNN networks. So he took the images which stay in 100 dimensions, learned over it. It has a lot of nonlinear layers. So the layers can learn a manifold representation, which typically these kind of probabilistic maps cannot, simply because with much lesser data points, apparently these kind of autoencoder systems can learn these manifold representation. And once they have learned that, you can put it back into a t-SNE plot. So apparently this is again an open thing. Not much has been done. If you are interested, this is something interesting to do. I am interested personally to do it for genomics data. By definition, it is not possible to theoretically reduce high intrinsic dimension. We have the intuition for that because I was giving you that little example, right? And there are other things. So if you do have that kind of a thing, just cut your loss. Bad luck visualizing such piece. You cannot do it. Third weakness of t-SNE is that t-SNE cost is a non-convex. We discussed this. There are methods which are LLE, Isomap, diffusion maps, which are convex. I will just add something quick here. Diffusion maps are essentially random walks in n dimensions, random walks in some high dimension space. So you have the data points and you're kind of jumping from one data point to the other with some Gaussian kernel. What they have in this paper is that they did have a random walk version of the t-SNE, which I did not discuss. So this random walk version of the t-SNE has overlaps with the diffusion map kind of idea. So that means this is then kind of an interesting thing, that if you are ever interested to figure out like transition times from your data record, so maybe financial data or this kind of data where you have price which is jumping from one time to the other, and you somehow want to figure out this transition matrix, the diffusion map is the most obvious tool, but there is a kind of a backdoor connection to t-SNE which is there in the paper, so you might like to look at that. There is a prescribed list of hyperparameters which I kind of put on that practical t-SNE slide, but the argument is that various seemingly different data sets have been visualized effectively using the same set of these hyperparameters. So that kind of solves this non-convex problem, like that even though it's non-convex, worse visualization, producing worse visualization is not better. It's better to have t-SNE with optimization parameters producing better visualization. That's what we conclude. Technical pitfalls, most of that we discussed. These are a few. that t-SNE is slow. t-SNE, as it was developed in this original paper, is slow for n greater than 10 to the power 3, and it's impractical for more than 10,000 data points because it was order n square. So after that, when the 2014 paper came, it kind of cut down the attractive interactions to only 3p nearest neighbors, and for repulsive forces, it uses a specialized approximate technique which sort of loses a little bit of the cost. So the cost function for close points is made a little less than it should be, and by that you kind of lose your low dimension embedding efficiency by a little bit, but you do make your algorithm order n log n, and so it scales very nicely to up to 10 to the power 5 points. This is what is typically what, if you use like a black box scikit-learn, this is what it will do. But what I suggest you to use is t-SNE, which is a method which essentially replaces Barnes-Hurt approximation by a method where you essentially do a fast Fourier transform in the Qij space and then calculate much faster. This scales up to 1,000,000 points and it's super fast. So it's kind of an interesting thing to play around with. If you are interested to dig into the literature, the way to do it would be go from SNE, then look at the classic paper that we did. This is the Barnes-Hurt approximation paper. In 2014, 2017, there was this paper which essentially made it a fast Fourier transform paper. And then there are 3 articles which essentially can be accessed without reading any of this, just if you are interested in the practical aspect of it. Look at the scikit-learn manual, which essentially tells you to do PCA before, and these 2 are interesting articles. This is a little lesser known by Kobach and Behrens from Germany. They focus on single cell genomics data, but they basically tell you everything about the t-SNE that you need to know and all those learning parameter and exaggeration techniques. And how to use t-SNE effectively is a blog kind of just to make you understand that don't just look at the clusters and be happy about it, because there is lots of things that can be going wrong around it. I don't think you learn much in terms of, if you're doing project building, much out of it. Outlook, retaining both local and global structure is extremely hard. This is while simultaneously reducing dimension of the data. Honestly, it is impossible if the data is really high dimensional. Strategy is always to choose a distance metric. First try linear methods, then try non-linear methods like t-SNE. Does not work, then try basically UMaps. So this is something which is kind of the latest in the field. We have seen this plot, and finally t-SNE is a fancy mathematical tool, a mathematician scatter plot, which is a man scatter plot. Okay. So that's it. That's all, and thank you very much for being here.